Very good. Thank you. Thank you very much, Gustav. Thank you very much to IDAM and to the Icelandic Welding Society. It is my honor to be present here in name of Aalto University, where I come. I am professor at Aalto University at the Department of Mechanical Engineering. I am presently the head of the Engineering Materials Research Group. And the subject of my talk will be on something that is not as usual to listen in these courses. I will try not to give a very fundamental lecture speech at all. So anyway, we will start by some fundamentals on solid state, and we will address during the fly some applications on dissimilar materials, which this solid state, although very old approach, is represented in this chart, the full field of techniques that we use to process the materials, to join them, to cut them, to eventually coat them. So everything is here, and when I present this chart, I should start by saying that if you understand this, you understand everything. So all the energetic activation that you have here, the mechanical energy and the heat energy represented here by the temperature and the pressure, the contact pressure, defines a window of application where we need to apply to overcome the stability of the materials. So the materials have this superficial and internal equilibrium. That's why they exist and they don't interact, fortunately. And so we need to overcome. Almost all the techniques that are addressed right now are in this line over the melting temperature with no mechanical energy. We have the resistance welding with mechanical energy and fusion. And then we have a large scope of solid state domain. And within this scope, a very particular important field is the viscoplastic third body. Third body because it lays between the liquid and the solid, where the material behaves as a liquid, but retains the mechanical properties, namely the shear strength and so on, as a solid. So in this chart, we have capacity to understand how this balance between mechanical and heat energy can result in joining. And forging is, in fact, the first. Forging and brazing are the first techniques applied to join materials. Why? Because before high power densities or enough power density to overcome the physical properties of the material to transport the energy, namely the thermal conductivity. So without this high power density, if the energy applied was below the critical capacity for the materials to flow the energy, when we reach the melting in some point, almost all the material would be melting. And so the limitation was big, and forging was and brazing were the solutions to do that. Nowadays we have, fortunately, very versatile techniques based on electric arc, electromagnetic laser, and mechanical electron beam, and also the chemical combustion. So the forging is in the heart of joining of materials, and what we need, and these guys know it very well, is plastic deformation and creation of new chemically active surfaces, heat and temperature, pressure and temperature. So before there was capacity to apply the plastic deformation that would generate the heat had to be applied before to enable the plastic deformation and activate then the joining mechanisms of diffusion and atomic bonding. Okay, we have something to learn with this group teamwork in our individual attitude nowadays. So these guys knew a lot about solid state welding, I believe, and then when the temperature was coming down, they had to apply the heat source again to be able to apply the deformation that will create new chemically active surfaces where the pressure and the temperature then enables the joining. So forging is in the heart of the most ancient applications of joining, but is also the solution for many high demanding and high value applications nowadays, where this similar joining of materials is one of the fields. So we will evaluate, I will present in a very brief summary the amount of solutions in solid state, and then we will focus on the friction-based techniques. We will address applications and some important industrial issues on the friction stir welding, and also then on the variants of this process, and eventually, even more important, some other options for material processing based on friction stir. So, coming back to the important diagram where all this mechanical and heat energy lies together to enable us to address a wide range. Now I just kept there the techniques that we have as more common to use in the solid state domain. So below the recrystallization we have this cold pressure welding, important for some welding of copper and aluminium wires. Then with a liquid interface, but just enabling us to activate, getting rid of that liquid interface, we get the chemical active surface and the temperature that enable us to reach or to activate the diffusion and the atomic bonding, depending on the level of pressure and time. So we have the high frequency welding, the flash, and a variation of flash which apply to stud, which is the stud welding. So these are the liquid interfaces solid state welding, because there is no solidification responsible for the joint, just to enable to reach the chemical active surface, getting rid of the original surfaces. But then with the bulk plastic deformation, more or less, we have the diffusion welding, ultrasonic welding, explosion mostly cladding, and then the friction-based technology. And this is this viscoplastic domain, this third body domain, is a very important field, as you will see, for innovation and opportunity to solve the remaining boundaries of engineering challenging materials application. On the field of the friction-based technology, I will start to present some of concepts that are all based in the same. So we generate plastic deformation. That plastic deformation generates the heat as it is triggered, and the pressure then enables to promote the joining mechanisms of diffusion and atomic bonding, depending on the range. So here we have an extrusion concept, enabling to join this swarf of aluminium into absolutely new sound material with excellent properties, thermomechanically processed. We have this friction hydropillar, which it's one of the best examples to address the solid state. It contains a very interesting concept, how the material flows and progress and generates the heat. And I emphasize that most of the heat is generated by plastic deformation and not by any kind of friction contact. That just triggers the plastic deformation. And here you can see also friction riveting. In fact, I have some components with me, and I may, as the time comes, this is an example of a rivet of metal to polymer joint, a very dissimilar ultimate condition, and I can send these over you. Please don't push it too hard, because obviously it's cut in half and may come apart. Also within this field of friction-based technology, we have this bulk plastic deformation of the friction rotary welding, where the friction triggers the plastic deformation, and the plastic deformation then generates the new chemically active surfaces with the pressure and the temperature promoting the joining mechanisms. We have very important applications that we deal with every day in our automotives and many others. oops, wrong direction. And oops, here. This is another very similar example of the same triggering of plastic deformation, now applied typically to light alloys like titanium, extremely complex to reach high performance in the joint zone. So we have a thermomechanically high performance now. The friction flow drilling, the friction surfacing here, where we deposit a consumable rod over a substrate. Here we are depositing 316 stainless steel, an austenitic stainless steel over ultra strength steel of 900 megapascals yield strength. And this was a gift to Rautaruukki that now is part of SSAB. You can see down on the right side multipass for producing some additive manufacturing of a rail that is also important in materials difficult to joint and to create these high value components, and the production of functionally graded materials, FGMs, by including some special particles with dedicated operation. So this is another recent invention based on this same concept, that we are able to produce tubes with continuous or variable shapes without any dies in materials that don't even exist in the market. Okay, this is an example of that, and we are setting up a company based on this, and you are very welcome to make any question on this regard. And coming to the friction stir welding, so these were friction based, and one of them is a distinguishable process. This friction stir welding came as a result of tests done by Wayne Thomas at the Welding Institute, and it was patented for the first time in '91. There is a first application that we will address in '95, and so friction stir welding is an important process with several variants, but also bringing up new solutions for processing materials. Here you can see the application of the concept. I believe that many have seen these, if not directly. So we have a non-consumable tool that has a shoulder and a probe. The probe promotes the steering of the material because there is no need for preparation, and as you see, there is no emission of radiation or no need of filler metals or shielding gases. Okay? We reach very high performance. The material is thermomechanically processed, is forged as the best materials, as the base materials are operated, okay, and produced. With this process, significant number of impacting applications are now set up. We will address some of them, but first I should say that the standardization exists. It is being revised now for more other alternative control techniques, including the temperature control, but also for operation, because the demands for operation here are quite different in terms of qualification from the skills for manual welding in electric arc, as an example. So I think that more important than the process for you is to understand the applications and the scope of this. So the first one was, and shipbuilding was a big important field to fly this process into the real world, if we can say so. So SAPA and ESAB had a very important role in this scope. We can see also applications they run now in train industry, where also Promeco in Finland is a distinguishable company producing friction stir welding for over 15 years, and including several applications in the train industry. Applications in automotive industry. Here you can see some wheel rims produced in Europe, in Australia. Also some components like the tunnel frame for the Ford, for Audi, also Mercedes has some components also included in their chassis systems, and including different materials and different thicknesses. So tailor welded blanks are a very important concept here. And for the first time, there is a plane, an airplane that has structural welds, or components are welded with high structural responsibility. This Eclipse 500 is a very well-known application. And very recently, ESAB has produced for Boeing and NASA this vertical assembly center with 61 meters high to produce the hydrogen and the liquid hydrogen, liquid oxygen tanks for the propulsion system of the next generation rockets. One impacting application, because it's a fancy one, if I can say so, behind the importance of his, results, is in the field of production of computers, and Macintosh is using friction stir welding for the new generation iMacs, and it's playing a very important role in being able to address thin structures with low distortion when you have already sensitive components inside. And one application that I was responsible to merge residual aluminium coils into new coils for Siemens to be able to produce heavy-duty transformers. So we were bringing down the remaining aluminium that was not able to produce one more coil, but the requirements for welding was quite important and quite strict, mainly on distortion, but also on electrical and mechanical performance for bending and for not being a hot spot. So we were loading multiple coils and welding them together until a volume was retained. So we were bringing aluminium from a value of residual aluminium into a value of market aluminium. Okay? But the amount of applications nowadays are quite wide, and companies like this Riveting in Germany are applying friction stir welding in food, building services, medical devices, and for thermal management. Another important field, I would say a key one in the history of the industrial application of friction stir welding is being tested, but soon will be implemented by Posiva. It's also been developed in Sweden by SKB for the 50 millimeters penetration of copper oxygen-free phosphorus component to weld the lead to the cylinder that are the corrosion protection barrier for this nuclear fuel and waste that are inserted in pellets in cast iron. This is a very important first time in the world that a proper procedure for storing is being implemented with very high safety capacity. And as an application example, I want to emphasize two that have been recently implemented at Aalto University. For automotive industry, joining aluminium to steel is a holy grail, optimizing the lightweight, corrosion resistance, and energy absorption capacity for repairing of the components and so on. So very important, is an industry that is always pushing the boundaries, and we have developed a new joining concept promoting the conventional lap joint with some clinching mechanical joints. So we were taking advantage of both physical, chemical, and mechanical constraint. Multipass weld has been implemented and tested. Optimal conditions have been reached for these, and we have new solutions now learning from this implementation that are willing to get partnerships to go into more focused applications. Very important always the control of the intermetallic compounds between these dissimilar materials, and we reached very low levels of aluminum in these intermetallic compounds, which is the best conditions, and also a layered structure that performs very well. So overcoming the problems of high temperature processing of the materials where these intermetallic compounds compromise the joint. A similar application, now in a different scope, the joining of copper to aluminium, also challenged by the difference in properties, superficial and physical internal properties, namely the melting temperature, but also the thermal conductivity. And objective here is to produce bus bars, optimized bus bars, where the ends typically are connected to copper components. And when we have bus bars in aluminium, there is a challenge related with the maintenance. So the first thing that we were able to implement here, and I have the pleasure of having one of my excellent students that participated in this research and was the main responsible to lead, Dagur Olafsson, that is present here in the room. What we investigate as a first step is why to do these tips in copper to add to the bus bars body in aluminium. And we found that the maintenance needed, the force relaxation at the tip when we use copper or aluminium, it's quite different with a life in terms of retaining the clamping force double from the aluminium. And so it's quite important, and the investment has a big return immediately on the maintenance of these bus bars connections. Here you can see the team that has implemented, also this work was sponsored and oriented for Promeco, a company in Finland. The very important profile of mechanical clamping with chemical joining activation in all around the joint. We can go in detail into this. This slide emphasizes the condition in terms of offset of the tool in relation to the original line, the position that delivers best mechanical properties is one where the tool is more into the aluminium side, and only a small part of the probe processes the copper. This enables to have a balance between the amount of energy that is generated and controlling also the intermetallic composition and the thickness, the intermetallic compounds. Most of the tool is then does on the aluminium side. And what you can see on the right side is that the temperature in the aluminium side is lower than in the copper. So the issue here is that the power source are the materials and not the friction, because most of the tool is over the aluminium, and if the friction was the source of the heat, then the aluminium would be hotter. Okay? But because the higher internal energy of the copper, you have higher temperature. So this is an important issue. We have this friction word in the title, and but it is the plastic deformation that generates the heat and the new chemically active surfaces. Another important result was the electrical performance, and we obtained with the welds an electrical performance that is 200 times higher than a very high, about 40 kilonewtons load high clamping load. And this emphasizes that the weld will never be a hot spot compared to any kind of bus bar connection. So continuing now in the variants of this friction stir welding, other options to improve these results, we will see the stationary shoulder. It's one of the best solutions to implement now a shoulder that don't rotate, is stationary, and only the probe rotates. This provides a better surface finish of the contact of the tool with the material, but also reduces the heat input and provides the heat input through the thickness in a more equilibrium way. And is one of the biggest trends now to apply the friction stir welding. Also bobbin tools, when we don't have access to both sides and the anvil is a problematic component to extract, then we can have two shoulders and use this bobbin tool concept. Another concept that has been developed in my research group, in cooperation with a research group in Portugal, was this assisted by Joule effect friction stir welding tool, where we are able to overcome the remaining oxide layer by the distance of the tip of the probe to the anvil by processing it with localized heat generation using DC current locally. The complexity of the solution is the other hand, but that's the problem of many advanced solutions like hybrid laser welding. Also, the complexity is one of the disadvantages. Alternative wider processing with an instantaneous shape of the shoulder that minimizes the force can be implemented with a lateral movement or with a skewed movement around the focal point, or even with double rotational eccentricity of the tool in relation to its original rotation axis. We can also have to homogenize the sides, because like in an airplane wing, we have more material flowing in the shear side, so in the advancing side, in the retreating side than in the advancing side. So to homogenize this difference, we can have this re-steer, where the tool rotates here, as an example, with 10 rotations per each side, okay? At a very high rotation speed. Different rotations like a static shoulder, but here slower shoulder rotation. And to overcome the complex clamping, we can also have twin steer, where the tools compensate the lateral forces and we discard the need of heavy clamping. So we have addressed some of the friction stir welding variants, and now we will see some friction stir based variants. Among these, the embossing, where the viscoplasticity, this liquid as behavior of the solid material, flows and is able almost to take our fingerprint when we leave it in the anvil. Okay? So it flows and is able to take shapes, very complex shapes, during the viscoplastic flow. Also, as many other joining methods, we are able to produce additive manufacturing concepts. Processing the surface of the materials for casted components is one important opportunity to overcome internal defects, but also to deposit and distribute particles to have a functionally graded surface. One field of important development nowadays is this friction stir spot welding, where there is no melting of the components, and the spot exists, as we know, in resistance spot welding. This is achieved with 2 rings and 1 probe, 1 body. The middle ring and the internal body goes in rotation, opposite rotation, and vertical movement, and compensate the flow of material. This viscoplastic flow of material will have a penetration that overcomes the top thickness and enables the full spot joint. We have new standards that are almost ready to be applied in the multiple variants for this friction spot welding and friction stir and so on. And at Auto, we have now a new concept for the original friction stir channeling. We are able to open channels inside of components and take it closed channels and take it in any path, like a hole inside, but with any kind of free path, and also with free shape and changing the shape. The great jump has been recently when we are now doing this with the capacity of welding. So we are merging, we are joining different materials or same materials and able to open channels in one of the components. So this is a great opportunity for thermal management, and as you see here on the right, we have the internal channel. The performance of these channels are very high compared to any circular. So I would say the circular shape is the worst one because you want to increase the amount of surface per unit of volume that is liquid volume or any kind of heating or cooling media. So we have a non-circular shape, but also very rough, which increases not only the surface, but mostly the turbulence effect, increasing the heat transport capacity. So this is one application from a company a startup company that we have set it up very recently in classic cars that are modified from original combustion engines into electrical solutions by a company named Retro EV. We have a partnership with them, and we are replacing the original cooling that is heavy, relatively expensive, and by a higher performance based on this hybrid friction stir channeling solution. Here you can see the extraction of the material from the inside, creating the channel paths in a complex shape that is able to access the shape of the batteries as they were disposed in this battery pack. We are replacing here 2 cooling plates by 1 cooling plate, and we are using the copper as the cooling unit that has very high thermal stability, corrosion resistance, and very high capacity to flow the energy. So it answers much faster than the aluminium. And then the aluminium is cooling the copper. And because we need only a very thin copper, we can remove the aluminium from the zones that are not needed, we have a very lightweight solution also, which again is important for anything that moves. This is the implementation of LENAC. As you can understand, this channel written the other direction, and that's the concept. Here we have the implementation and the installation in the electrical battery pack, and it's running. It has been in exposition in several countries in the last couple of months. And I have some of these channels that I can also, I'm sorry, I forgot to flow them, trying to keep, you have hybrid channeling of aluminium, and aluminium copper, okay? And finally, I will show you a new solution here in this slide of, again, ultimate capacity to join aluminiums to polymers, okay? With a mechanical high load-bearing capacity that is not depending on the environment as alternative solutions for joining metals to polymers are. So here we extrude the aluminium into the polymer, and the polymer fulfills the empty zone, and we are able to produce now continuous joints, okay, between aluminium and polymer. Okay, again, this one you can make forced, but this one don't. Okay, it's cut it in the half. It may break. All right, and I pretty much came to the end. It was a fast overview of many solutions. Each one of them has its own challenges, as we have in many of the fusion-based processes. I would say that these techniques based on solid-state welding and processing are in permanent advance since many centuries ago, resulting in a wide range of solutions. They include mature solutions and more modern breakthroughs, including some of the most impacting innovations in this, our WWW world of welding. All right, thank you very much for your attention. I would prefer not.
Okay.
Okay? Yes. Please don't take photos from the samples.
One question, because I was interested in, it looks like you're using basically a mill.
Yes.
Like it will go forward and press
Yeah.
down. But you only use spare material, or you also add welding material?
Okay, so we in fact use the degrees of freedom of typical degrees of freedom of a milling machine and the typical capacity of a press machine. And we compose both in one machine with alternative control methods. So the milling machine is able to control positions, eventually some speeds, and we control beside that the force. So we are able to apply also under force control, position control and speed control, the movement in all the directions of the tool.
Yeah, but
with capacities of 10.
The plates, is that the only thing that's melting together? Or
There is no melting here.
No, okay, but it's kind of flowing together. But
Depending
I
on the
think
solution,
this
yes.
will, can you also add
Filler material.
Yeah.
Yeah, there are solutions where filler material is included in the shoulder and is added to the processed zone. That is easily implemented if you give me the opportunity to come back in the tooling solutions. It's a little higher, I believe. Maybe after this, I'm sorry. Oops. It's in the variants, yeah. In the variants. So if you take a look on this stationary shoulder.
I think we lost the screen.
Your face was funny when I was moving this and you. Why? Is this enough to get it there? Computer. Aha. Sorry. I was trying to show you, if you remember, the static shoulder concept. Okay? In the static shoulder concept, you can, in fact, easily add filler metal as the shoulder is not rotating. You can compensate and you can create new shapes, in fact. There are solutions for that. There are solutions for many things. The creativity here is a limitation. Lots of solutions exist and many more are to be invented. That's exactly the message that I want to leave with this presentation. This is an extraordinarily important field of creation of new solutions for dedicated applications. Not a flexible process that is able, like electric arc, to access multiple and easy way a joint and a challenge. Because here we need clamping and dedicated devices for solving the issues. Yeah. But then the level of quality and productivity and is able to access the same in steels. Applying friction stir welding probably to plain steels doesn't make any sense. We have extremely good solutions. But for ultra strength steels, for steels that have a composition that is not possible to maintain with fusion-based processing the original properties, then solid state is a great opportunity for dissimilar materials also. Like what is important for a welding engineer is to be able exactly to understand the techniques with this energetic chart that I showed from the start and to select the best solution and not the one that he knows. We can discuss later on, obviously.